All right, good morning. Let's start by talking a little bit about programming assignments 4, since everybody might have questions. Any questions on it? How's it going? Have you successfully done problem 2? 1 is just pen and paper, and then in 2, I think there's a pattern to my program assignment. First you derive with pen and paper, and then you do it. This whole thing here, you just copy paste. Of course, this is one test example, and you should be able to figure out what problem I'm solving. And you should just confirm that it looks good enough, comparing to Rangikata 4. I mean, do you all realize that there are 2 for loops, for example? I mean, maybe that's a little tricky, but remember, we have one for loop taking the steps, right? And inside that for loop, for each step, you have to make a Newton iteration. So maybe that's, and you got to name things, right? I don't exactly suggest what to name this thing here, but we do suggest I here. So if your outer for loop is I, just like a good old RK4, you need another, let's say, K or something to do the Newton iterations. All right? And if you're really stuck on this, and now I'm talking about problem 1, of course. I mean, implementing it should be easy if you, that's just MATLAB. If you're stuck on problem 1, they do something similar in the book for actually a more difficult method, the trapezoidal method. But they really have a whole page in chapter 511 on how these Newton iterations look. So look at that. It's actually just a very small modification of that. And then implementing it is, and then you try this to test it. Then 3, I believe, should be fairly straightforward. And I mentioned again that I fixed this bug last time. That's what the number you want to use. All right, so no general questions. Maybe you guys are busy, so you will all. You should probably start early with programming, because as you know, debugging can take forever. Unless a homework where you can always spend a finite amount of time on each problem, programming might just not work. But all right, we have office hours after this too. We can talk more if you have specific questions. The schedule here is that I have nothing scheduled for next week. We'll go through stuff. Please comment on what you want to review. MATLAB codes we should probably look at a little bit. I know some people are just using them without maybe knowing every detail of them so much, and that's an important part. So that's what we're going to do for now. We're finishing up everything, or chapter 6 now, by this special types of matrices. It's still review, and again, I'd like to hear how much review it is. I don't know. I guess it's less and less review as we get further along chapter 6 here. And I'll point out what's numerical about this. This was a big numerical part that you probably might not have seen before, except maybe some of you in 110, but definitely not in Math 54. So what did we say here? Well, we did all these properties of matrices. We did determinants. I don't have too many things to say. Yeah, question? No, the final is on everything, yeah. Especially since I have the rule that the midterm score I could skip, right? So if I said that I didn't cover the midterm, people would just not come for half a semester, right? And then, so maybe if you really look at the weighing of all the problems, I need to make sure we cover what's after midterm 1 well, right? So maybe slightly more, but no, it's really pretty cumulative. So next week during the review, maybe we'll go back to floating point arithmetics and Taylor and start from the beginning. I don't know if I have time for that in the review, but yeah, it's going to be everything. More final questions? It's on Wednesday, the May 15th, right? Yep. So don't miss on that. What? May 14th, thank you. 11:30 a.m. I don't know. Oh, I actually know where we are, but I don't know, or I haven't written it. I mean, but it will be a different, because this room is too small. So the. Oh, good. Thank you. It's in Hearst Gym. I'll update because this room is too small. More final question, practical question. Well, we have all of next week for that, right? Now, just my concern is to make sure you can do your homework for next week. Determinants are a review, I'm sure. This slide is just how to compute or define a determinant. Here are a bunch of properties that I think you all know. How do you actually compute a determinant? That's a tricky question because in Math 54 type classes, you probably use the definition directly and expand by, for example, a row. And they even teach you tricks like finding a row with many zeros, make it easier, etc. How many terms are there in this definition? So a 1 by 1 is just a scalar, right? The 2 by 2 are 2 terms. The 3 by 3 has 6 terms. Already there you should see a pattern. Continue the sequence, 1, 2, 6. But, as a mathematician would say, the answer could be anything after that. So you've got to do one more. A 4 by 4, it's going to be expanding along one row, so you get 4 terms, right? And each of them is a 3 by 3, which was 6 each, right? So it's 24. And now you see the pattern. It's factorial, right? So the answer is that if I ask you to compute a determinant for a 3 by 3, you probably will do the 6 terms. If I ask for a 10 by 10, you will definitely not do it. Probably already at 4 by 4. 5 by 5. I don't know where the threshold is by hand. It depends on the numbers, right? But the truth is that to compute a determinant, if you really want it, you use some other technique. In fact, if you look at all these properties, they remind a lot of the Gaussian elimination, but they're about determinants. There are some important things here. For example, adding a multiple of another row to a row, let's see, I here. If you're adding a multiple of a row j to a row I, you don't change the determinant. So that means you can do all of Gaussian elimination and the determinant stays the same. Okay? Except if you flip rows, then you know from the volume interpretation that this is going to happen. You're going to negate the sign. You're going to flip the sign, right? So that's basically it. And if you actually want to multiply a row by lambda, you also scale the determinant by lambda. But if you think about it, we never really did that in Gaussian elimination, necessarily. We just subtracted multiples of rows, but we didn't really scale rows. All right, so how does that give you? So I just told you that a determinant doesn't change. But how do you actually get the determinant? Well, that's the last part I here, which you can prove very easily from the definition that the only terms surviving, if you have zeros below the diagonal, are the diagonals. So that's something you know already, and it's quite straightforward. I also mentioned that we actually don't use determinants much in numerics. It's used as a mathematical tool for basically defining what it means with invertible matrices and equivalency there. I did mention that a small determinant, an extremely small determinant, does not necessarily mean that it's almost singular. And my example of that was 0.1 times I, which is a great matrix. If someone asks you to solve 0.1 times I equals the right-hand side, you should be very happy because you just multiply the right-hand side by 10, and everything is extremely well-defined. There is no loss of precision. It's a great thing. But what is the determinant of 0.1 times I? Well, it depends on the size, right? But if the size is just a modest 1,000 by 1,000, the determinant is 0.1 to the power of 1,000. It's a really small number. You cannot look at determinants and say small means bad. 0 definitely means bad. But as you know, in a computer, things are never really 0. Anyway, this is a variant of the fundamental theorem of calculus. We'll look a little bit back and forth. Fundamental theorem of linear algebra. Wrong class. Well, what's good about having a non-singular matrix is that AX equals 0 has no non-trivial solution. Of course, AX equals 0 has always the solution X equals 0, and non-singular means it has nothing else. That leads pretty easily to the fact that AX equals B has exactly one unique solution. You can invert it, and this is equivalent to having the determinant non-zero. Here's the new numerical part. Gaussian elimination works. Okay? So this shows you that one way to prove that a matrix is non-singular is not to compute determinants or inverses or trying to solve something. You just go straight at E. You try to do Gaussian elimination. If it didn't work, it was singular. That's probably the most straightforward and easiest way to figure out. It seems like it's not the way we teach it in lower level classes. Then we first compute determinants, and if it's equal to 0, we're smart, and we don't do all the work with Gaussian elimination. But in the real world, Gaussian elimination is the cheapest way to even just find out that it didn't work. Of course, you need row exchanges. If you doubt that ever, think of a simple example. How about 0? Anything 0 here, right? Can be non-singular and as good as you want. 0, 1, 1, 1. But as soon as you have a 0 there, Gaussian elimination will break unless you do row interchanges. So this theorem says with row interchanges. In particular, it shows that if things go bad with Gaussian elimination, if you come here and that's a 0, things then go really bad with Gaussian elimination without row exchanges. In fact, you're dead, but we never do that. We have to do row exchanges in general. But things can still go bad if all of these are 0. Okay, but then you can show easily, and we didn't do that then you must have a null space there, a non-trivial null space. You have a singular matrix. So it won't go wrong. That's what the theorem is saying. All right, here's a big numerical thing. This is big in numerical linear algebra. We actually like to write Gaussian elimination as a matrix factorization. And it's really just expressing the fact that everything you do in Gaussian elimination can be written as matrix-matrix multiplication. Realizing these things just is a big practice in matrix-matrix multiplication, to realize what's going on. We did say, for example, that this matrix here, it looks a little funky. It's identity, and then I put a bunch of numbers below the diagonal. If you just do it by hand, you realize that the identity will, of course, do nothing. It will just reproduce what you had before. But then each of these m's will grab, it will hit row number, if you multiply from the left, it will hit row number k. Okay? And it will multiply it by that number, and it will add that to row number k plus 1, k plus 2, etc. Just do the matrix-matrix multiplication, and you can see what it's doing. So all of these m's will be multiplying row k of the matrix to the right. That's because they appear in column k. That's how matrix multiplication works. They will take the result and add to the corresponding row, namely k plus 1 all the way down to m. Okay? That is Gaussian elimination. In fact, if you choose these m's as the multipliers from Gaussian elimination. So what we've said here is that one step of Gaussian elimination is m of, let's say, 1, m parenthesis 1, the first m, multiplying the A matrix. And we did all this, and we could see we zeroed things out. And then you keep on going, and you get a lot of these m's multiplying each other. And the end result, of course, was a lot of notation here. This is just in order to, I can't keep on calling it A, right, because I mess it up. So it's just a notation. I know by hand, when you do Gaussian elimination, you do the arrow, and then you keep on going, right? And we don't write the equal sign, of course. It's not equal, because we mess it up. We do this operation. But if you really want to write equal, you have to make new names. So you could define A parenthesis I here as being the I matrix after this process, right? So in particular, AN is, then you've done n minus 1 steps of multiplying by these m's. N minus 1 steps of multiplying m's, yeah. And we all know that the goal of Gaussian elimination is to make it upper triangular. So this is what's going to happen. And that's kind of good, because now we've expressed the process as a matrix-matrix multiplication. And the only next goal here is that it's a little messy. There are a lot of matrices there. I promised you to write it as a neat little A equals L times U, right? So we got to combine all of these. And these were these things that were a little magic. First of all, you got to bring it. You want to bring it to the right-hand side. We multiply A from the left. Remember, we have an A here, and we do all of these operations, M1 all the way to Mn minus 1. And the end result here is what I call AN, but of course we know it's an upper triangular, so I'm going to start calling it U. Okay? And this is a matrix factorization if you want to. It's just not very beautiful. One bad thing is that there are n matrices here. That's not nice. We should definitely combine them into one. But another thing is that, if possible, we often like to write A equals and a product of matrices. So I'd like to both combine them and bring them over to the right. Okay? And it's going to eventually become an L. So I want to define an L that is the inverse of this thing here. And you all know that that's going to be the inverse of each of these flipping the order. So that's expressed here. Let's go slowly. Each of these has an inverse. Turns out that you just flip the signs. We did numerical examples by little matrices, and I said that you could really just, if I propose an inverse to you, it's very easy to prove that I'm correct. You don't have to do any magic. You just multiply them, right? So if you just take this here, and then you take the m, which is the same with minus signs, and multiply, you'll see, whoa, it's identity matrix. So it's not hard to prove. Then in this statement here, they say that now you can define an L to be the product of all of these, and when you multiply together with the right-hand side, you get A back. Okay? They didn't actually prove the big thing that multiplying all of these together actually puts all of these little m's together like this. Okay? So that's the next magic fact. The first magic fact was that the sign just reversed when you inversed. And the next is that when you multiply them, they just put themselves at a nice spot in this matrix L. So U is not really strange. It's really what you're done with after Gaussian elimination. L is also very easy when you know it. You just put all these multipliers at the right spot. And you're done. That's the A equals LU factorization. We're not doing row interchanges. We'll do that next. But this is the most fundamental step. Why do we do this? What was the reason? It's not really anything fundamentally new over Gaussian elimination. It's just a nicer way to express it. It's the way you want to do it in a computer code. If you want one good motivation, I mentioned, what if you have a lot of right-hand sides? And you don't know them beforehand. Then we taught you in Math 54 that you compute the inverse. And every time you get a new right-hand side, you just multiply instead of doing Gaussian elimination again, right? We can do that same here, but inverses are horrible. It's a little beyond the scope to talk about what's bad about them, but they're just bad, bad, bad. You don't want inverses, while these are good. And of course, this is the same thing, that if you do pre-compute, remember this is, I say pre-compute, but it's because it's an expensive operation. This is the ordo n cubed type operation, right? And then I keep on feeding you right-hand sides and ask you to compute, to solve ax equals, let's say I'm putting a number there just to show you that I'm going to do it many times, right? Then it's easy to do. It's not quite as easy as just multiplying an inverse. I mean, matrix vector multiplication is pretty easy. But here it's actually back solves. It's just that for a computer, it's not that bad. So what you do is that you first, you of course just plug in LU. And what you're going to have to solve first is going to be L times a Y. I think I called it Y equals V1. And then you solve U times an X equals this Y. And guys, if you basically, I get this by just replacing A by LU. And then first you solve L times something equals the right-hand side. And that something is, of course, U times X. Right? So, so that's the motivation for now for why you want to do LU factorizations. How about row exchanges? You need to know about it. It can also be expressed as a matrix-matrix multiplication. And we like to write this in the following form. Actually in a nice way like this. To be honest, here people actually put it on the left because it turns out to be that way. So many times people refer to this as PA equals LU. So this is really the form you want to use. Of course, you can multiply over the P to the right if you want to. And what is P? You can flip rows by multiplying by matrices. Okay? Matrices can do a lot of things. So in fact, you define this so-called permutation matrix where you just put a single digit 1 per row at the right spot, and zeros otherwise, you get a permutation matrix. And you've probably seen them in linear algebra, I think, before. They have some interesting properties. Its inverse is, for example, its transpose, which you can easily convince yourself of. If you multiply from the left by one of these, you will flip, or you will reorder the rows according to the permutation. But in particular, if the permutation matrix is really just a flip, which is what we usually do, so here's one type of permutation, where you have your ones, and at some point, you decide to flip row I and j. What you do is that you just do the same thing here, and you flip these. Apart from that, it's an I, right? So here's a permutation matrix. You can get it by really just taking identity and flipping 2 rows, right? Multiply this from the left. Multiply a matrix A by this from the left. You will flip rows I and j. So it can be expressed in that form. How do you flip 2 columns? Is it a different matrix? Can I flip 2 columns, ij, with this? What do I have to do? Also matrix multiplication question. We don't do it here, but there are factorizations doing it. But we never flip columns the way we do it. You multiply from the right, and that you can convince yourself of that. It will do then it will flip the columns instead. Anyway, we just flip rows. The only little issue here that is not described in the book or in my slide is the fact that it's kind of tricky because, remember Gaussian elimination, we're doing this throughout, right? I mean, we do it maybe the very first step, but then we do some L's or some M's, and then we do it again, right? So really, if you want to write all of this out, it's going to be A. The first thing you do is multiply by a P, right? Then you do one of these M's. And then you have to do a new P because you always want to make sure that you pivot up the largest number to the pivot. So you really get PM, 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 PM. And the third stroke of luck when I teach this to the grad students, which we really go through the details, is that it actually separates out. So you can still put all of these M's together in an L and all of the P's together in a P. And it kind of comes because permutation is a very simple matrix in a way. But it's not something we go through. But it's not clear that that's going to happen. Anyway, one way to interpret this is that if you magically could figure out exactly all the permutations that have to be done, you could in principle just do it, and then it's just back to the old case. That's how you can interpret it. But this is the form you use in any software. MATLAB, I mentioned last time, they try to hide the p from you, but it's really there. And they try to help you not doing the p. I think you know that in MATLAB, you really don't doing this at all, because you just do backslash, right? If you want to solve a linear system ax equals b. But of course, under the hood of backslash is doing this. But what if you want to do this problem, solving a lot of them? What if I tell you, you're going to write a little MATLAB code, and it's going to be running in real time or something, right? And I'm going to feed you right-hand size, and you're going to solve them. If you do backslash each time, it's going to take forever, right? While if you, let's do a little demo for that. I always fail my demos, but this I can't fail, I think. Or I always fail my timing demos. Because if you do, here's the right-hand side. So solving this takes a certain amount of time, right? Okay, so that's not too bad. But imagine bigger, or imagine that you're going to do this a lot. Each time you get a new b, you're going to redo Gaussian elimination over and over. That doesn't make sense. Given that the most expensive part is in doing the factorization, and actually solving is not too hard. So how do you actually do that then in MATLAB? You pre-compute LU. And I mentioned last time that you can use this form if you want to. It's really very unpedagogical, because there is a p, and they just put it into the L. But given that they do that, we kind of stuck with their notation. We could put the p there, but let's just do it. So this, of course, takes about the same time. Okay? Because the majority of the part for backslash is the factorization. Now, as you get new b's, you can just do x equals not a backslash b. You want to do this, but that's already factorized, so you want to do this. Okay? So how do you do that? Well, first you get to solve with L, then you get to solve with U. And in MATLAB, a way to say that is first solve with L, then solve with U. Let's put spaces so we see it. Okay? So you can convince yourself that that's, I mean, an easy way to see where this comes from is that backslash can be read as inverse. We never produced inverse, but one way to read backslash is multiplication by inverse, right? So if you put A equals LU here, first you do L inverse, then you do U inverse, which means U inverse applied on L inverse B. So it's quite easy to remember that. And my point was that it will do the same thing super fast. Oops. Not a big difference here, but as n goes bigger, this cost, you remember when we did the operation count, back substitution was only n square basically, right? While Gaussian elimination, reduction to triangular form, was n cubed. So the bigger n gets, the bigger this difference gets. Anyway, that's one motivation for LU. There are a lot of, much of numerical linear algebra is about studying other types of factorizations. This is, of course, one of the most famous ones. You can write A equals a lot of different things. Eigenvalues, which we are not going to discuss in this course, but you know about them. They also can be written as a matrix factorization, which I think you know. It's called diagonalization. That's actually Math 54 material. So factorizations are quite common. Anyway, let's move on with the new stuff here. This is about special matrices. They're not that special. They're extremely common. And the reason is that they show up in nature, in particular symmetric matrices, but also something called positive definite matrices. And then we start off with diagonally dominant. These are important. I would say in real life, people solve linear systems. They are very often special cases. So they're not that special. But of course, if you take a random matrix, it's not likely to be one of these guys. So let's look at some properties that you may not have seen before. Have you seen this term? Strictly diagonally dominant. It's almost obvious from the wording, from the name, what it means. It means that the diagonal is kind of dominating the matrix, but it's not clear exactly what dominating means. It means that it's greater than the sum of all the off-diagonal entries. Okay? So an example would be 5. Let's make it just diagonally dominant. 1, minus 2, 0, 0, 3, 3. This is diagonally dominant. Okay? Not strictly. So of course it's not defined there, but diagonally dominant, you include the equal sign, right? What you do is that you look at each diagonal entry, and you look at all the sum of all the j's, not including I. So you look at all the other elements in the row, absolute values, right? And you add them up. So 3 plus 2 equals 5. Check. Now you look at the 2. 1 is less than or equal to 2. Check. Now you look at this guy. 3 plus 0 is less than or equal to 3. Check. So this is a diagonally dominant matrix. If you put minus epsilon there on the 5, it's not diagonally dominant any longer. Or if you put plus epsilon here, where epsilon is positive. What's good about this? Here's a really nice one, actually, for, again, maybe kind of stupid homework problems, where you're supposed to think before doing. This immediately tells you this property is really easy to check, right? Compared to everything we've done. You're not actually calculating much. You're just adding things up and checking something. This implies non-singular matrix. So that would kind of be fun to give you guys a 5 by 5 with messy numbers and ask you to figure out if it's non-singular. And you might go for determinants, which is a mess. You might go for Gaussian elimination, which is a mess. But this might give it away immediately. Notice that it's only implication in that direction. A matrix can very well be non-singular and not strictly diagonally dominant. But you could at least figure out that it's non-singular by doing this test. Well, another property that is not clear is that then you can do Gaussian elimination without row interchanges. That's also a nice property. Let's just look at the first property. It's pretty easy to show. It's how come that this matrix is so good that it's going to make that property nice? So actually, in this case, this matrix would not qualify because the theorem talks about strictly. My example here was not strictly. Here's how you show it. So strictly diagonally dominant matrix A is non-singular. All right? We'll do contradiction, and we'll assume that it's singular. For some x that is not 0, right? That was the fundamental theorem of linear algebra. Now it's a little bit of trick. You can actually look. This is really just looking at. You could figure this out by writing out the matrix vector multiplication and see what this means. But the trick is going to be to find the largest number in this x by absolute. Okay? So in notation, I'm going to say choose k such that you find the kth entry of that x. And I know it's not going to be 0, right? Because x was a non-zero vector. So there must be at least one number somewhere that is not 0. And it's going to be the largest of them. This is where math notation sometimes fails. It's trivial to say in words what I mean, and it's how we have to write it. Sometimes we say the argument that maximizes the vector here, and the k would pop out. But the maximum itself just pops out the value. But of course, what I mean is just take your vector x that's, according to our contradiction, made this ax equals 0 without being 0 itself. Find the largest number. And the index is k. Another trick is to consider row k. Of the equation. And you just write out matrix vector multiplication. Okay, so that gives you sum of, remember matrix multiplication says row, usually we write an I there because we consider row I. But I want to emphasize that this I is really the magic k that was the largest number of that x, right? And then you loop over the j's multiplied by x. And that has to be equal to 0. All right? I know that I want to turn this into something that looks a little bit like diagonal on the left and everything else on the right. But you can see that a little bit where I'm heading here, because all the pieces in this definition of strictly diagonally dominant appear here, right? I am looking at one row. And that, of course, is called I in this theorem, but here I call it row k. But let's just isolate them and move the diagonal part to the left, or keep the diagonal part on the left, and move everything to the right. Everything else to the right. Then we get a minus sign. We get a sum of everything except k of a kj xj. Right? So apparently we're saying here that, it starts looking there. It's actually, it's equality, and there's this x. We're going to turn this into something showing that thing up there. Okay? Or actually the opposite, because we're going to do contradiction. Now triangle inequality on this, right? We take absolute values. We want to kill things off. And of course, there's a sum on an absolute value. You can replace it by just putting absolute values on everything, but then it becomes less than or equal to, right? The shortcut theorem. If you walk from here to there, it has to be longer than going straight, or something. Maybe that's not the perfect analogy, but let's do it. So triangle inequality. Inequality says that you put absolute values on everything, and of course, a product of two numbers, absolute value, is equal to the absolute value on each of them product. But now you get less than or equal to just because I split up the sum. And then you get this akj absolute times this xj absolute. And these are all the j's except the diagonal. All right? And akk is a nice number. Or xk, sorry, is a nice number. Because I know it's not 0, because there was at least, this is the largest element by absolute. So I can divide that down and say that akk is less than or equal to the same thing times this ratio here. And this was for all the j except the diagonal again. And now comes the trick. Why did I choose k to be the largest? Because all those numbers are less than or equal to 1, right? So this is less than or equal to just sum of akj for all the j's except the diagonal. All right. This means that A is not diagonally dominant. And what is the final reasoning? It was a proof by contradiction, right? So assuming we made no other errors, we might have. We've seen all those funky proofs where they tweak in a little error or dividing by 0 somewhere in order for you to draw the wrong conclusion. But assuming everything was correct, the only thing that must be wrong is our assumption. X equals 0. So this is contradiction, which means that A is not singular. Right? Kind of nice. Again, I cannot use that on this matrix, although there are other theorems that would tell me that this is non-singular. But if I just take a random matrix, of course, it's not likely to be in any way diagonally dominant, right? What are the odds that all of these guys should be greater than the sum of all of these guys? Here it fails immediately, right? So in general, you cannot do it. But if I really want to produce something, I could do something like this. If I add much, I'm sure this satisfies, but you could check it, right? I added a lot on the diagonal. And here I know immediately that this guy is not singular. But I have to check it, of course. But you see I have 5s and 6 here, and these are like 1. I mean, when you do random matrices, you never know. Actually, this one is close. A4. Let's take the absolute value of that last row and sum them up. Oh, wow. Do you see what happened here? My example did not work. Because this guy is actually less than the sum of these guys in absolute. Right? So that was bad luck. Let's do it again. Now it looks great. I'm sure that one is fine. So I had bad luck with the. So then if you, what I'm saying is that you can quickly check, and if this is satisfied, you know that it's non-singular. Anyway, more properties. This you've heard about before, I'm sure, in particular when it comes to eigenvalues. We won't talk about eigenvalues here. We'll talk about positive definiteness anyway. The definition is really just that for every non-zero vector, x transpose ax, this quadratic form, x transpose ax, is positive. Let's see. Yeah. Just maybe one little confusion here, that in other courses, I'm sure you talked about SPD matrices, symmetric positive definite. And when those courses talk about positive definite, they mean the same property, but not necessarily symmetric. In this course, it's defined to be a symmetric matrix, but they don't put symmetric in the name of the property. Okay? So it's all good. It is symmetric positive definite matrices. They're just not going to call them that. So the only thing I'm warning is that don't think that they're not symmetric. According to the definition, they are symmetric if they're positive definite. Otherwise, we don't say they're positive definite. So that's a somewhat abstract formulation. You know that it's connected to a lot of things. It's connected to, well, we'll see in the next theorem that it's connected to positive pivots in Gaussian elimination. It's connected to positive eigenvalues. That's usually what we refer to. But computing eigenvalues is, of course, not a practical thing. But physically, there are a lot of things conclusions you can draw. It does also imply that A is invertible. So there are many things you can do from it. One way to check, just to look at this form that you've probably done before, but just looking at the form, one way to check it is to just write it out. So let's see what I have here. So X transpose AX, what is this? It's a number that's implied from the theorem, but it's pretty clear that it's a number because A times X is a vector, so this is a dot product, right? So it's a number. That number you can write by doing matrix-matrix multiplication twice, or actually matrix vector and then vector vector, right? But if you write it out, it ends up being a double sum, of course. So let's say that the first one is I, and the next one is J. Then you're going to get combinations of Xi and Xj. Like that. All right? If you want, you could use this on a matrix. Let's say this guy. 4, 2, 0, 2, 8, 1, 0, 1, 1. Okay? Note that this is actually not strictly diagonally dominant. You cannot use the previous theorem to tell that this is non-singular. It's one of those borderline cases. It is symmetric, so it makes sense to ask for positive definiteness, right? If this was unsymmetric, if I put a 1 there but not there, and I ask you, is this symmetric? Is this positive definite? You would say no, because according to definition, such a matrix has to be symmetric. But let's just write it out. X transpose A, X is then, and you list all these terms according to this. And of course, you've done these before. You get the diagonal elements coming out like this. The cross terms get a factor of 2 of them because they appear twice. So you get 4 x1 x2. Then you get the 8 of x2 squared. Then you get 1 plus 1 of this guy, x2 x3. Sorry, x2 x3. And finally 1 of the x3. So, you know, you've probably seen in various courses, we call these quadratic forms. Obviously, they are quadratic functions of these x's. And the goal is to say that this is, if you want to show that this is positive definite, you want to show that this is greater than 0. Clearly, if x is equal to 0, it's going to be 0. That's not interesting. But for non-zero x, it has to be positive. And how do you do that? You know, a technique that we often do, not necessarily the best, but you cannot really tell, right? Because these are positive. That's great. But how do you know that these guys could very well be negative? And how do you know that they don't bring it down somewhere for some vector x to become negative? The trick is to write them all as squares, right? You complete the squares, and then you draw some conclusion. In fact, you want a triangular pattern. So completing the square here would give you complete squares. You get this to be, you take out the 4, you get an x1. And if you take out the 4 here, you get 1 of this mixed term that you get to divide by 2 to get an x2 half. And there's the square, right? Now, of course, I added too many x2s here. I didn't want that, but I better subtract away the square of this times 4, which is x2 squared, and then plus the rest. Plus 2x2 x3 plus x3. Right? Then you do it again because there's another one we don't like. So you take this here, equals, that one is the same. Here you have 7 of these guys, so why don't we just take out a 7, x2. And then we want an x3 that makes this equal to 2. We took out the 7, so we better divide by that. And there is a 2 there, so this actually works out. And if in doubt, just do your algebra. And when you multiply these, you get, of course, 2 of these. That's multiplied by 7 and gives you exactly that. Now, of course, I added too many x3s. You got to bring out, take away a 7th of this x3 cubed. And then finally, we have the x3 cubed that's from before. All right, now I'm done. Let's just, I'm not going to write it again. Let's just say that this here is 6/7 of x cubed. Okay? Why does this show me now that this must be a positive number if x is non-zero? These are all squares, and it has a triangular pattern. If I just gave you squares like this, you don't really know, right? They could cancel out and become, well, you could show that it's 0. But we got to show that it's positive, right? So it's true that a sum of squares, certainly you know it's not going to go negative. But you got to show that it's positive if x is non-zero. And if you just look at these guys, there could very well be x3s, x2s, and x1s that make these guys to 0. So the triangular pattern is the key here, that this here only has an x3. Right? So that leaves that in order to set this to 0, let's say you want to make this equal to 0. I claim that this whole number here, is greater than or equal to 0. Unless, let's try to make it 0. So clearly x3 has to be equal to 0, right? Because it's a square there. But then this sum here has to be equal to 0. And x3 was 0, then x2 must be equal to 0. The next equation gives us that. This implies that x2 must be 0. And then you go up here and say then x1. So the triangular pattern allows you to unwind it like that. Or in other words, x is the 0 vector. And that is the proof that this is a symmetric positive definite matrix. Sorry, I said symmetric. Positive definite. All right? So that's probably how you might have done this if you saw this before. It's actually a way of doing it. The amount of work is comparable to Gaussian elimination. So it's not necessarily worth doing in a computer. It doesn't really structure it in the same way, but you could do this. But it's very closely connected to the Gaussian elimination, what we just did. Let's look at some properties. You know it has an inverse, so now I know that this matrix is invertible. Here's a cool property. The diagonal elements must be positive. And you can see it directly from the definition that if this number here is positive for any x, it means in particular that all these diagonal entries are positive. Okay? Can you see why? Suppose I put a -4 here. What x would contradict that this matrix is positive definite? Remember, this is true for all x, right? That this is positive. So let's look at that. What would, where did I put that? You got to choose the right x. There's a magic x that will, if I make that 4 into -4, it will return a negative number. So, OK, so positive definite matrix implies positive diagonals, OK? Let's see why. Well, you got to think about the structure here, right? Look at all of these terms. It's completing the square, right? If I just grab an x that is equal to 1 at one spot and 0 at all the other ones, then this will be 0. This will be 1 only when I equals j equals that spot, right? So I can pick out one single a here by setting x equal to a vector with a 1. I can pick out the diagonal element. It will return a I. OK? And if that is negative, clearly it violates the definition of the positive definite. So in other words, you pick this vector x, which is all 0 except at position I, where you put a 1. OK? this gives that X transpose AX, just plug it in or just do the matrix or whatever you want to do, picks out this number. Right? And you just told me it was positive definite. That means that that's since positive definite. Quite easy to see. You just pick the right X. Again, this might be a nice way to quickly figure out whether a matrix is even worth. In fact, this is done in MATLAB. We'll come to a code soon where there are codes that need symmetric positive definite matrices, and MATLAB does a quick check on the diagonal first to just rule out if it's even worth doing by this. So it's a kind of a practical test. The next property says what? Again, the notation is confusing here. I would say the largest element shows up on the diagonal. Certainly true for my matrix. You can prove that again. It's a little by choosing the right axis. Let's do the last one. Here's a nice little combination of two A's on the diagonal, AII and AJJ. And the product has to be greater than the corresponding off diagonal times each other, which of course is the same as square because it's symmetric. All right? For 2 by 2, this is of course just the determinant being positive. Do you see that? For 2 by 2, A11 times A22 minus the other ones, that is determinants, right? So that's a statement here. But it's more general. In more general, it's going to show up for any matrix if you take any two I and J. Let's see. Another smart choice of X will give that to us. Namely, so let's see, A of ij square is less than the product of these. Okay? For any pair of not equal A and I and J. Okay, you got to pick the right X as well. It's pretty clear based on the proof I did there that you want to talk about I and J and nothing else. So you should probably think of a matrix X that is 0 everywhere except I and J. That will pick out these four numbers, right? You could try once. It will probably not lead exactly to where you are. This is the trick that you want. You want to choose an X that puts an alpha at I and a 1 at J. Okay? And I'm just going to write that to not mess it up. But I mean 0 everywhere else. Right? And then you look at this expression. And now, of course, you get 4 terms, right? Remember, with just that guy, you just popped out AJJ, which in particular showed that has to be positive, right? Now we're going to get 4 terms. So those 4 terms are going to be, you're taking II multiplied by alpha square. You're getting 2 of these multiplied by 1 alpha, the off diagonal. And you're just getting AJJ as before. And it was, well, for positive definite A, right? It was positive definite. So you're telling me that this is greater than 0. And apparently this implies that. Yeah. That's probably true. The way to see this is that this is a polynomial in alpha. And you can actually solve it. And what you'll see is that there should be no zeros and no negative numbers, which means that the discriminant in the quadratic formula has to be negative so that everything goes complex. The same thing as this curve, so to speak. This in alpha, this function, this quadratic in alpha stays above 0 all the time. So that's the trick. This implies that the discriminant is negative. Okay? Otherwise, you can't have no real solution to this equation. And that discriminant is 4aij square minus 4aiijj. You just plug in your quadratic formula here, however form you remember it, and you get this expression out. And that has to be negative. And that leads to the theorem. Just moving things around. Right, pretty easy to get these out. A little tricky to just figure out which x to use, but when you do, it comes out. So I guess, again, this could be a practical check for whether matrix. But now it gets complicated because this would be how many tests? The tests I said before, this would be just looking at all the diagonals, and if they're all positive, there is still hope that it's positive definite, right? That's what it means. If you find any diagonal entry that is negative, it cannot be symmetric. It cannot be positive definite. This property, of course, you would have to check n times n minus 1 pairs of numbers. So that's a little bit more of a mess. Here's another term that you might have heard about. Leading principal submatrices. It's pretty obvious. Submatrices, let's go through terms here one by one. What is a submatrix? A submatrix is, we never really define, but it's kind of what you do when you do the colon operator in MATLAB. So taking out a chunk of rows and columns would be a submatrix, right? So that's not too interesting. Principal means that you always start at 1 and you go just up until a certain level, in this case k, and that makes it a principal, namely starting from the beginning and not skipping any rows. So, sorry, that principal means that you stay on the diagonal, that you pick a certain number of rows and the same number of columns. Leading means that you start from 1. Anyway, these words put together, it just comes down to very simple looking at the upper k by k part of a bigger matrix. Okay? So here's an example. If you take this here, A equals same matrix as before, 4, 2, 0, 2, 8, 1, 0, 8, 0, 1, 1. The leading principal submatrices of this are the 1 by 1 matrix 4, the 2 by 2 matrix 4, 2, 2, 8, and the 3 by 3 matrix, the matrix itself. We have, these show up in various cases, but one theorem that we're not proving is that symmetric positive definite is equivalent to all of these having positive determinants. Isn't that interesting? So if you want to check that, you just do all of these. The determinant of A1, the first, that's the determinant of the number 4, right? Which is 4. And if this fails, you stop immediately. But it didn't fail. This is greater than 0. Then you look at the determinant of A2, which is the determinant of this guy, which is 32 minus 4, 28, right? And then finally, determinant of A3, that's just determinant of A itself. I'm not going to copy it. And that's, well, whatever way you remember this, 32, 0, 0, minus 4, also 28. Oh, I messed something up here. No, I get it to, yeah, minus 2. Good. And that's also greater than 0, okay? So you look at all of these, and that implies that it's positive. I mentioned before, this is certainly not a practical way to do it, but if I give you a 3 by 3, it's probably the fastest way to figure it out. But there's a big difference between reality and bigger matrices and what's easy to do by hand. Why do we like determinants when we do small hand calculations? I mentioned this already back in the divided differences in the Newton form, where the Newton form seemed quite messy for you guys, and I still said people think it's a simplification. It's because people don't like to divide by hand. Okay, and all these calculations, we're not really dividing when we're computing determinants. That's why you think this is easy. You're probably willing to do even a 4 by 4 using this method. But Gaussian elimination, there's a lot of divisions and weird things going on. So it's not practical, but it's a nice property. All right, here are a bunch of theorems. Okay, so I mentioned before actually that, so of course all of these things, remember we had, if we just focus on positive definite, we had the nice property here that it's invertible. Okay? So what does that mean? That means that it has, remember I had a theorem before saying Gaussian elimination with row exchanges will work. But it's actually stronger. If you know this positive definite, you don't even have to do row exchanges. And this is important in practice because it means that it simplifies the method a lot. Doing those row exchanges seem easy to do by hand, but it's actually quite a mess. So a property we have is that positive definite is actually equivalent to being able to do Gaussian elimination without row exchange it and getting all positive pivot elements. No zeros showing up. The stability is that this refers to the statement I made with my 10 to the minus 20 example, where things didn't quite work out. This will never happen for positive definite matrices. So it's kind of a nice case. You want to do Gaussian. If you can work with positive definite matrices, your numerical analysis becomes much easier. Now, following up here is that since you have positive diagonal elements, you can pull out a D here, which is a diagonal matrix. This is a new factorization that is quite common, and you probably have seen the last one called the Cholesky factorization, but let's stay on this middle one here and see how we can actually do that. So what it's claiming is that if it is positive definite, and then you're able to do LU. We knew that already, at least with row exchanges, but now the first theorem up there told us that you can do it without row exchanges, so I don't even need a P. The permutations are not needed. Now they're telling me that all the elements on the diagonal of U are positive, in particular non-zero. Do you all agree that that means I can write L times a diagonal matrix with those numbers and a new U twiddle here, which is just dividing away those diagonal numbers? This you have to think a little bit about, but what I'm claiming is that if you have a matrix, okay, and it's upper triangular, I want to make those ones. And I can do that by pulling them out and multiplying from the left, and then I get my ones there. And something else here. My notation with the crosses here is confusing because these x actually change, while these are actually exactly those. But let me describe it. You have a U here. You know what it means to multiply by a diagonal. Again, this is just matrix multiplication. Multiplying by a diagonal matrix from the left will scale the rows. This number will multiply this row. This number will multiply that row. Do you know how to scale the columns? Multiply from the right. You remember what I said? That was the flipping matrices before, the permutation. Same thing. But now we're hitting the rows. Okay? So that means that clearly the number here is going to be equal to these here are going to be equal, right? That's what I mean by you can pull out the diagonal of a matrix like that and put those equal there. And the rest is what it is, right? Anyway, so I claim that you can take that out and you get a U here. Now, this U twiddle has the property that it has those ones on the diagonals. What do you think U twiddle must be if A is positive definite? I should use the word symmetric positive definite because that's what I like. Well, it's the symmetric part that I'm thinking of. If A is symmetric and you do that, there are not that many choices for you. PD implies symmetric, right? That was in the definition. So that means that LDU twiddle transpose is equal to U twiddle transpose D transpose L transpose. And that has to be equal to the matrix itself. All right? Now, what is the transpose of a diagonal matrix? It's itself, right? So this means that U twiddle transpose D L transpose equals L D U twiddle. And it's actually not a full proof, but it's a pretty clear indication. You can actually show easily, since these are invertible, they have ones on the diagonal, that you can start multiplying from the left, etc. These must match for this to work. So U twiddle there must be that matrix. And then, of course, it will match this as well. This means that this U twiddle is equal to L transpose. And going back here, you really wrote it on the form LDL transpose. Okay? This simplifies your work, your storage, a lot of things. It means that you don't need L or U. If the matrix is symmetric, and in fact it's very reasonable. You had a symmetric matrix. It's really just half a matrix. If you tell me a symmetric matrix, you don't have to tell me the whole matrix. You tell me half, including the diagonal, right? So when I factor it, it wouldn't make sense that I produce a lot new information and do both an L and a U. And indeed, it doesn't. The L is the same if you just take out the diagonals. So that's a nice property. Just to show that it works, a little simple example of this LD L transpose, or LDL factorization. Let's do the same matrix as before. 4, 2, 0, 2, 8, 0, 0, 1, 1. Okay, so you just do Gaussian elimination. You leave 4, 2, 0 alone, and you subtract by half of that row from there. So you're getting a 0 there. You're subtracting half of this. You get a 7 there. And this was a 1, sorry. And you keep your 1. And this I haven't come to yet. Now you want to subtract a 7th of that row from this row. So you're getting 4, 2, 0, 0, 7, 1, 0, 0. But I'm subtracting a 7th. I'm getting 6/7 left here. Right? If you wanted to do LU, this is U. And the L, we all know, is identity plus the numbers that I multiplied by to do this, with the convention that you subtract the rows. So to put a 0 there, I subtracted half of this row, right? That's that multiplier. To put a 0 here, I did nothing. Same thing as subtracting 0 times the first row. But in general, it will be there. To put the 0 there, I subtracted a 7th of that row. Means that you get a 7th. Right? And we've done this already, and it leads to this leads to A equals LU. You can confirm what the theorem told us. First of all, that it worked, but more importantly, that you got positive numbers on the pivots, and then of course it works. Then nothing can go wrong. Let's do the LT, the LD, L3T now. So now you define this matrix D. And as I said before, you really just pull out those diagonals. This is D. Okay? And I could, in a way, I'm done. Based on my little motivation from before, I'm done. I have L, I have D. This is the factorization. But I want to show you that it's the case. So U, as we defined it, remember U had to be the diagonal. I split U. I took out the diagonal D. And left, I get a 1 here, right? Like I promised. But of course, here I have to divide by those numbers. So you get 2 divided by 4, which is a half. Here you get a 0. Here I pulled out a 7, which means that I must put the 1/7 there to make it agree. But all I'm saying is that the U you produced, I'm pulling out the diagonal elements and fixing up the other ones so that this is the case. And I can always do that. Okay? Now, of course, you identify that this is L transpose. But you don't have to do this calculation because we know it will always happen. So this means in particular that A is L, D, L transpose. A very nice factorization. All right, one more part. OK, we're greedy. We don't like that D. It was LU before, and now it's LU, L transpose. It's unclear. It's half the storage, but it's look a little ugly. Can we do this? And by the way, the notation is confusing here because this L is not the same as that. That would be weird if it was. How do you do that? What I want to do is that I want to put this D over in L, so to speak, right? But there are 2 L's. So I better split it into a product of 2 numbers. I better take the square root of those numbers. Send 1 to the left and 1 to the right. So let's do that for our example. and you take your D. I'm going to call it L twiddle this time. And you know, the reason they don't do there is that if you know this is what you want, you wouldn't even define the previous L, but we got to keep them apart now. And I claim that you get it from this. Define L twiddle to be L times, and remember, I have this, right? I want to eat up D. I want to incorporate half of D into the L. And by symmetry, the other half to this L, right? So basically, to diagonal matrix, you could, actually, there is a square root of a matrix. You probably saw that too in Math 54, at least 110, that you could take the square root. But the diagonal matrices are much easier. Just write this as the product of square root of D and square root of D, right? And you bring one to the left. So I claim that if you put these together like this, square root of these numbers so again, I scale. Actually, I'm scaling what? Rows or columns of L? Now you're getting your column thing, because I'm multiplying by a diagonal from the right, which means I'm scaling the columns of L. Not that it matters, but that's what we do. So you can compute this, and you're getting 2, 0, 0, 1 square root of 7, 0, 0, 1 over square root of 7, square root of 6, 7. All right? All right, and now the last part is that it is now clear to you that this means that A is LD L transpose, but it also can be written L twiddle transpose. Might not be immediately clear, but if you plug in my L twiddle here, it becomes L times this funky matrix, right? And then here you have it with transpose, which means it becomes the transpose of that times L transpose. And the two of these multiply together to produce the D. This is extremely practical. It's called Cholesky. It's not, I don't know if it's mentioned. Factorization. And it's really almost as commonly used as LU. The reason is that I said that a lot of matrices in real life are positive definite. So, I mean, it's not fundamentally different. It's just that you only have to worry about one matrix. You only have to store one matrix, etc. So that's what we get out of that. All right. Last slide, actually. We talk about band matrices. This is another special, it's completely different now. Just a different type of special matrix. A big part of this is identify things that have a lot of zeros. And the band matrix is such a matrix. So I think I told you before that I'm solving things with 100 million degrees of freedom. You can pretty easily convince yourself that that sounds impossible if I didn't make some assumptions. Because if you take a matrix with 100 million degrees of freedom, how much memory do I need to store that? I need this number of entries in my matrix, right? And I need 8 bytes per number. Remember chapter 1.3. Make it 4 if you want to be cheap, whatever, right? But this is kind of what I need, right? You need this many bytes. Okay? And I don't know how well you know supercomputers. That's a pretty big number. Your computer has typically order of gigabytes, right? Which is 1 in 9. This is 10 million more than that. And it's actually not that insanely far away from, but no, most supercomputers don't have this memory. I mean, it's not like many magnitudes away from what they have, but it is a little too big. That's not the problem. The problem would be that if you work on this, for example, solving AX equals B, it would be cube on that. And that would mean that it's basically, let's say just cube this number here. This is the number of multiplications you need to do, remember? Or divided by, or times 2/3, right? Do you think a supercomputer can do 10 to the 24 multiplications in a decent time? I don't know if you read the news, but they talk about all this competition. The big countries are competing about the fastest computer. And then, a few years ago, Japan had the fastest supercomputer. Then America, Livermore immediately built a bigger one. And now I think China has the biggest one, right? I don't know, but they're competing. And I mean, the numbers they throw around is petaflops. I think that one in China is 12 petaflops or something, right? Why I would have such a matrix? Yeah. So I invert these all the time. We need those matrices. It comes from solving differential equations. And if you're solving the airflow around an airplane, for example, and you start putting little grid cells and velocities everywhere, it just scales insanely. And so it's easy to get 100 million. But my punchline here is that we're not doing it this way. But anyway, if you want to use the fastest computer in the world to solve this, let's say they do 10 petaflops per second, you would need this many seconds, which is, divided by, this many days, right? 3 years. So no, you cannot solve that in this way. It's by far, and that's the biggest supercomputer, and we're using more electricity than Berkeley, I think, or something. I mean, it's just insane. So why do we get away with it? We do sparsity. So my matrices, what if I tell you that my matrix actually is very special, and it looks like this? It has something there, but then it has a lot of zeros. And then it has this pattern where it has really just 5 bands. So you have the diagonal. Here's the diagonal. OK? Oh, I messed it up. No, here's the diagonal. And I have 2 bands on top of that, and everything else is 0. Are things changing now? Well, storage, of course, changed a lot. I mean, it doesn't look like, it looks like half X's and half zeros here, right? But imagine that this is 100 million. I went from 100 million square to just 5 times 100 million, right? And same thing here. This is a so-called band matrix. The good thing is that when we want to solve these big systems, we get structures like this. Much more complicated. It's not like there are zeros everywhere, but they are sparse in the sense that you have zeros almost everywhere. But this is one particular easy case. You define upper bandwidth 2, lower bandwidth q. And you can actually find, as the slide says, you can find efficient methods for this. A band matrix is just defined by this. Tridiagonal sounds very obvious. It has 3 diagonals. That matrix there I would call a pentadiagonal matrix, because it has 5 non-zero diagonals. Everything else is 0. Now you can do Gaussian elimination on this matrix. We always do that in the grad course. Like how is it, and it's not cube any longer. In fact, it scales more like a square. So now suddenly it's quite doable, and it's quite easy to do. So we can solve those systems, much more complicated systems on just smaller supercomputers. What is the last property here? A tridiagonal matrix is a special case of really just having 3. And they show up a lot, too. Not that much. I don't know why they emphasize it. Partly it is because we have these special properties where you can figure out whether it's non-singular by just looking at these numbers easily. But that's a special property. But this would be a great, you know how I said a few times, this would be a great programming assignment, but we don't have any more, so unfortunately. But a typical homework assignment I would say probably half the courses in the world teaching elementary numerical analysis would ask you to write the Gaussian elimination, the Gauss elim that we wrote before for this matrix, for general P and Q. And the reason is not that it's fun or anything, it's just that it will really force you to understand every step. Because all those i's and j's and k's that we played with, that went from +1 to n, etc., they are changing. So it's kind of a fun project. But here it's just more a side note. Maybe there was a homework problem, but not too many. Anyway, questions on this? This was pretty new, right? Maybe not the positive definite part, but I don't know exactly why. It's a mixture of linear algebra and numerics. That's how they teach it. All right, so don't forget your program assignment and homework to be due by Tuesday. I have office hours now, and next week we do review. Thank you.